technical problem. So I will talk about a small introduction about X-ray free electron laser and their relationship with high brightness beam. This is a basically impossible talk to give in 20 minutes. I've given like some sort of this pedagogical talk before, like for example for the higher XFEL lasted 1 hour. So of course you're not, you know.
Of course it's possible. We'll see.
Yeah, exactly. So, but maybe next time for this pedagogical talk we should have a little bit more time.
Twice
So,
as fast.
Twice
as fast.
No, I just took out a lot of stuff, and the fact that this is like, I think a function of the pedagogical talk is to give a lot of references. And so, whatever I'm not saying, I think there is a lot of nice lectures on the subject, and this is where you should go for more detail. So what am I trying to do here? Describe what is an X-ray FEL, what are the key elements, discuss a little bit of the underlying physics, the basic property of the radiation from accelerated relativistic electron, and how you can combine all the emitted radiation to make a free electron laser. And at the end, I think this is the, try to highlight the connection between X-ray free electron laser and the goal of this center to generate higher brightness electron beams. So, of course, like XFEL have generated a scientific revolution in the last decade or so due to their wide tunability range, transverse longitudinal coherence, generation of X-ray with very high power, and a very short pulse length. Basically, the XFEL is pretty much the only instrument that can give at the same time spatial and temporal resolution at the level of the atomic scale, so femtosecond and like very good temporal resolution, spatial resolution. A lot of, for a good review of the scientific results obtained, for example, from the first XFEL, which is the CLS, there is a nice review of modern physics that came out just a few years ago. X-ray free electron laser, of course, like they first proposed in 1992 by Claudio Bellerini, which was my advisor. The first one was realized in 2009 at Stanford, when they used like 1/3 of the slack linac to feed into the undulator and generate coherent X-rays at the wavelength of 1.5 angstrom. After this initial success, there is actually, you know, believe it or not, in the last decade, 7 either soft or hard X-ray FEL in operation around the world, and more are being constructed and designed. So this is a field that is like blooming and expanding very quickly. And the reason for it, of course, is that if you compare the quality of the X-ray beam that you get from this X-ray laser is 9 to 10 orders of magnitude, measured in brilliance, which is like the number of photons per second per unit solid angle per unit area in a 0.1% bandwidth, and it is like 9 to 10 orders of magnitude larger than other X-ray sources that were previously available, previous of the advent of the XFEL. So this big improvement in the brilliance of X-ray sources, of course, generates a lot of interest. So let's try to understand how they work. And of course, like the way they work is a free electron laser radiating, the free electron radiating, and we have to go back to the theory of like how this radiation generated. And there is this nice app that, of course, like a picture here is worth more than words. I mean, there is a lot of conditions for which a particle can radiate. Of course, you need to have acceleration, or you can put the acceleration, the particle in a medium. You can stop or start the charge. Or you can have a near structure, like a periodic medium or close by. In general, the radiation can be broadband or narrowband, but in order to generate like a narrowband radiation, you have to impose some form of periodicity. Let me look. If you go online and you go to this website here, and I'll try to show you how this look. Right. So this is like a nice applet that shows you these are the electric field from a point charge. Right? So if the point charge moves, there is no radiation. But what you can do with your doesn't work. What you can do with your mouse, you can like move the point charge back and forth, for example, and you'll see that this radiation field can expand out. So you get,
cool. That's cool.
Yeah, the other thing that you can do with this, this is from Shintake's lab. You can set up, like, for example, a particle trajectory. So this is how you have to generate radiation. You have, of course, to accelerate the particle. You can, in this same device, you can look at what happens if you take a particle and you wiggle in an undulator trajectory. Now you have this particle, of course the field lines outside are just a straight electric field lines, like the relativistic pancake, but then as soon as the particle wiggle on this yellow trajectory, you see this radiation front that's being emitted from the particle. So this is actually one of the basic physics elements of free electron laser. You gotta have particle radiating. And the mechanism for which we are getting radiation out of the particle, of course, is this undulator magnet, which was developed like 70 years ago or something, like actually at Stanford, like from Motz. It used to proposed to use like a periodic arrangement of magnetic field in order to wiggle the particle back and forth and extract a lot of radiation output. In order to understand like what kind of radiation you generate from this FEL, you start from looking at the particle trajectory in this wiggling magnetic field. The BX, these are the magnetic field, like in particular we're interested in the BY, which is the magnetic field which is with particle moving in the z direction will oscillate the particle in the horizontal dimension. You can calculate the particle velocity, and the particle velocity is oscillating with an amplitude which, of course, if the particle is more relativistic, the amplitude is going to be smaller, it goes like 1 over gamma. But the other important parameter that comes from this analysis is this normalized undulator vector potential, which is the parameter K. K is the undulator vector potential, normalized, of course, to the electron rest energy, and it's a very important, it basically tells you how much you're wiggling this particle as it goes in the undulator. The other component of the velocity, which is the longitudinal velocity, in a planar undulator, actually, the longitudinal velocity is not exactly constant. You have this, it wiggles with with twice the frequency in the longitudinal direction. So that the electron rest frame, the motion is an H-shaped motion. In a helical undulator, which is a different geometry, the one in which you wiggle the particle not just in the horizontal direction, but for example in both in X and Y, then you do not have this figure eight motion, and which has the main consequences is that you don't emit only one spectral line, but you're going to have more also the harmonics. Let's understand what is the wavelength, or how you get the wavelength of the undulator radiation. There are a lot of ways of thinking about this. I think the easiest one is thinking about interference. So you just consider the interference between two rays emitted by the particle as it goes back to the, as it goes through a wiggling period. And of course, the difference in time between these two rays, optical path, will be given by the difference in emission time due to the where the electron velocity is there, and of course, like the angle of propagation. The other contribution is from the angle of propagation. If this is a multiple of the wavelength, then you can have constructive interference. So you can write this relationship for the wavelength that can be emitted, and just by expanding the cosine and writing, beta, the relativistic beta in terms of the relativistic gamma factor for the particle, you get to this expression for the wavelength of the radiation that you can emit, the peak of the wavelength of the spectral of the undulator. So this is all nice, but it's a single particle analysis. Basically, one electron going through this trajectory will emit a spectrum which is peaked at that particular wavelength, and it depends on the angle. Basically, this describes the physics of conventional X-ray sources, in particular third-generation X-ray sources, in which these insertion devices of undulator have been inserted into the rings. Let's make this the next step and analyze what happens when you don't have only one particle going through the undulator, but you have multiple particles going through the undulator. So you can go back to calculate what is the frequency angular distribution for an ensemble of electrons. And you would have to do this integral where you sum up over all the different electrons, all the different contributions. Now, we consider there is, each electron is actually going to have its own position and its own velocity. But let's consider at the beginning the case in which all the velocities is the same. The only different things in the electron is their longitudinal position. So there is a spread in the z part, in the z coordinate. So the beam has a finite longitudinal spread. So when you do that, the integral will be the same for all electrons, except that there is a phase factor. There is a phase factor that you can bring out this integral, this factor b of omega. So basically you have like the emitted radiation will be the single particle spectrum times n squared b squared. This is the contribution of one particle. A pictorial representation of what happens if you have a disordered state, if the electrons are emitting at all possible phases, you have the picture up in the left over there, and in which all the wave trains emitted from the electrons are randomly displaced. The intensity in this case goes like to the number of the electrons. So it's the single electron spectral intensity times the number of electrons. If you find a way to organize your electron beam radiator in a coherent way so that all the electric field emitted by the particle will be summing up in phase, then the intensity, so like this is what you do over here, this intensity will go like n squared. This is the source of all the gain. Right? If you can do that, the number of electrons in an electron beam can be 10 to the 8 or 10 to the 9, and so you can have available a large gain in the emitted radiation. This ordering parameter is called the bunching factor. Let us discuss now what happens when you have a spread in the electron position or velocities. How does the emission changes? We have only considered so far a spread in the initial emission time, in the longitudinal emission time. So let's go back to the formula for the radiation wavelength. You can see that the wavelength of the emitted radiation will depend, of course, on the particle energy, gamma, on the magnetic field felt by the particle, K, and on the angle that the particle is going through. Now, no beam, in an electron beam, electrons do not have all the same energy, of course. They're not always in the same position, and they have a spread in angle. So in fact, like this will generate a spread in the radiation wavelength. And you can take derivatives, and the spread in the radiation wavelength will depend on the energy spread of the beam. It will depend on the different magnetic field sampled by the electron. Remember that this K is a proxy, is a normalized magnetic field amplitude. And it will depend on the different angles of the particle trajectory. Now, okay, the energy spread, you have to improve the energy spread of the, you have to try to make an electron beam with a smaller energy spread as possible. But the last two are in fact connected. Because you can't have, for an electron beam, you can't focus an electron beam in a very narrow spot and at the same time reduce that angular divergence. So there is a finite area occupied by the beam in the phase space, that's the beam emittance. So these two terms over here, this would be minimized if you have all the electron beams sampling the same magnetic field. This would be minimized if you have all the particles going at the same angle. You can't reduce them both at the same time, they're actually connected. And the way we, in accelerator physics, we think about the spread in position of the beam and the spread in angle of the beam is through the emittance and the beta function of the focusing element. So basically the contribution to the effective energy spread, the effective radiation spread of the particle will depend on the emittance and of course and also importantly on the beta function, on the choice of your focusing system. This will come back when we analyze how the condition for free electron laser to happen. So the idea here is try to get this bunching factor to be large, right? So that we can take advantage of this very large gain in the produced radiation. And the analysis of the stimulated undulator radiation was first done by Mady in the 70s, and he actually analyzed this system from the quantum point of view, but it turns out that the system is fully classical, and that's what I will discuss as a classical system. So this is a picture of the first free electron laser experiment. So how can you get the electron to bunch together? The way to think about the FEL is it's not really a three-step process because everything happens at the same time. But the interaction with an electron beam with an electromagnetic field generate, as I will show, an energy modulation. This energy modulation, as the beam will propagate into the undulator, transform into a density modulation, as you see here. So at the beginning, you have a random distribution of particles. The interaction with a wave will generate energy modulation. This energy modulation slowly turns into a density modulation. The density modulation is the electron bunching. So now you have a large bunching factor, and you have a much larger electromagnetic field intensity. And this is an instability which will grow, and in fact, it will grow exponentially. So this is like the step, the ingredients of the FEL. You have energy modulation, then bunching, and then increased radiation. So in order to understand the system, you have two basically elements, or the way you can think about the two elements is the particles and the electromagnetic field. So I'll analyze first the equations for the particle, then the equation for the field, and then when you put them together, that's where you have the instability and the radiation growth. So in order to analyze the particle motion, you start with the energy rate exchange equation. Once you write it in a different way, you can recognize k over gamma, that's the velocity of the electron. You can recognize the electric field amplitude of an electromagnetic wave. And then it's proportional, this energy exchange is proportional to the sign of the ponderomotive phase, of the potential in the combined field of the undulator and the electromagnetic field. In fact, this ponderomotive phase, you see, it's the combined phase of the in the undulator oscillation and the electromagnetic field. The other equation for the electron, of course, a two equation system, is the rate of change of the ponderomotive wave. This is pendulum-like dynamics. If you get an FEL prize, you get a pendulum clock. Right? Yeah. That's classical, I think. What happens if you look at the Hamiltonian dynamics of the particle, you inject the particle, then you start getting energy modulation, and then as the system evolves, you can see that all these particles kind of line up at a particular phase. That's where it's going to give you the bunch. So what happens with the field? As I said, the equation for the field. You have to complete the system looking at what happens at the field amplitude. So the undulator emission, because you have this interference effect, is actually narrow banded. So most of the analysis, this is not necessary, but most of the analysis in the theory is done in the so-called slow wave approximation, in which you separate the field into a fast oscillation at the frequency of the emission and a slowly varying amplitude. And this is, in this sense, is slowly varying. Is that compared to the radiation cycle, this field is more or less constant. You can write then the Maxwell equation for the vector potential, change it thanks to this slowly varying level of approximation, and you'll see that, of course, the way the radiation evolves will depend on the current, and which is proportional to the beam density. The beam density, so if you make the spot size smaller, this is going to be better. The velocity, and then how much the particles are bunched at that particular phase. So this is the second step. The last step is how the bunching affects the generation of the electromagnetic field. So if you put all of this together, you have three equations. So, the equation for the evolution of the particle, the equation for the evolution of the energy, so the evolution of the phase, the evolution of the energy, and the evolution of the field. Now, of course, these equations are written in normalized variable. It was found out early in the development of the theory that you can normalize all the variables, so this entire system only depends on one single parameter, which is the FEL Rho parameter. Basically, for example, you can normalize the energy of each particle as the deviation from the resonant energy in units of this Rho parameter. What is this Rho parameter? It tells you basically the solution. Of course, if you linearize the system, it's an exponential gain. So it's the classical instability. You can even start it from a very small signal, or you can start it even from noise. the radiation will amplify itself. It will modulate the particle. The particle modulator will bunch, and then there will be even more radiation emitted. So this is typically what happens along the propagation along an undulator. So let's look at the Rho parameter, because the Rho parameter determines all the important elements, all the important physical quantity of the final radiation and the system. So
After that well bunched, there are some noise. This is the perfect solution, and still you have that some.
So the maximum bunching factor in a typical FEL is on the order of 0.6. So it's not 1. Right? So you have a lot of particles bunched at a given phase, but of course in the phase space there is no linearities, right? There is an S-shaped phase space, and some of the particles are actually not. Most of the particles are at the
So most meaning what? What fraction?
0.6. So
60%.
yeah,
So it's quite large, 40% outside of that.
0.6 is the average, but yeah, that's right. I mean, not all the you can, yeah, that's exactly right.
So that's intrinsic. That's the maximum you can get to.
There are some schemes people thinking about, for example, linearizing that that potential. But yeah, in general, 0.6 bunching factor would be, you know, the radiation would be, yeah, n squared times 0.6 squared, which is still a large. You imagine that you start with a bunching factor that is 1 over n, so 1 over, so 10 to the minus 9. So getting to 0.6 is already quite good. Yeah, the maximum ideal would be 1. Right? And there is schemes in which people are trying to put all the particles in that, to improve the FEL characteristics. Yeah, the gain length, which means like this exponential constant that will tell you how much the radiation is growing, is depending on 1 over rho. The saturation power is proportional to rho. The saturation length is proportional to 1 over rho, and the spectral line width is proportional to this rho factor. So in general, you can see that in order for the system to be shorter, more efficient, better, more radiation, you want rho, which is this particular combination of the plasma frequency of the beam divided by the, this omega u is just the undulator frequency, and the coupling is proportional to k, to the 2/3, is the coupling factor. You want to be that as large as possible. This is where the brightness contribution comes in. I'm just writing rho in a slightly different way, where I explicit like the dependence on the plasma frequency. So look at the dependence here. Rho, okay, there is constant beam energy. This is the Alfvén current. It's proportional to the current, to the 1/3, and inversely proportional to sigma x squared, to the spot size of the beam. So where in the spot size of the beam for a given lattice, it's proportional. It's you can write it as the geometric emittance times the beta function. So this is, you can extract, you know, everything else. I mean, there is energy, there is the undulator period and k, and you can certainly change that. But you can see that you can make rho as large as possible if you increase the beam brightness. Okay? So especially hard to get rho very large at very high energy. Right? And this is why which you need in order to generate X-rays. So in fact, in order to develop the XFEL, there, you know, 20, 30 years ago, there was a big push in improving the brightness of electron sources, and the RF injector that was developed by UCLA, by Jamie and Claudio, played a big role. Played a big role in this. Let me. I have a couple of more considerations that I want to make that are important. What are the conditions for this instability to grow? Okay. First, of course, the energy spread has to be smaller than the induced energy modulation. That's sigma E smaller than rho. This is another important one. The electron photon, the electron phase space has to be smaller than the radiation phase space. The radiation phase space area is lambda over 4 pi. The geometric emittance, this is the electron phase space, has to be smaller than lambda over 4 pi in order for this instability to grow. Notice that epsilon here is the geometric emittance. So the normalized emittance is epsilon times gamma. So in order to have a smaller geometric emittance, typically, what you can do, you can increase the energy of your accelerator. So a smaller emittance beam will let you radiate at the same wavelength with a lower energy beam by changing the undulator parameter. This is actually not very important, but it, of course, is like if diffraction brings out electromagnetic field too fast, then you're not going to have a lot of gain. Let me discuss these two plots. This one is a plot of the gain length for one particular cases, but what is important is the scaling, which are general. Plot of the gain length as a function of the focusing in the undulator. So if the focusing is relaxed, if the beta function is large, you have a large spot size. So not a lot of beam density, so there is not a lot of gain. Instead, if the focusing is very tight, you have a lot of focusing in the undulator, then the angles in the beam, of course, will be large, right? If you try to focus the beam, and so that generates an effective energy spread that also kills the interaction. So you have an optimum beta function. The important thing about this optimum beta function is that it depends on the emittance. Okay? So this minimum will shift depending on where your emittance is. So this is another plot in which I show the gain length as a function of the emittance. And they say, oh, of course, we want to improve the emittance, because by improving the emittance, the system will perform better. It will have a shorter gain length. But the caveat here is that this is optimized beta function. So every time you improve the emittance, in order to take full advantage of the better beam brightness, you have to change your focusing. Right? You have to optimize your focusing in order to improve the actual performances. This is an actual example. This is a very relevant example. It was one of the motivations why we had the Future Electron Sources workshop last year funded by the DOE. For an existing system, or it's not existing yet, but this is designed already. This is a 4GeV LCLS2 driven by superconducting RF cavity. Look at what emittance improvement by a factor of 5 will buy you. Almost nothing. Because all the system, the undulator and everything, was built in order to take advantage of this emittance. So you're not going to improve that much by simply improving the emittance. In order to take what I'm saying is that in order to take full advantage of the improved beam brightness, it's not just you change the cathode and everything is going to work better. You change the cathode and then you have to follow through the entire system in order to take advantage of the better beam brightness. So for example, like this will work well at 4 GeV to radiate at 5 kV, but the current sources, are not enough to radiate, for example, at 20 kV. So this is a big motivation for us, for the DOE also, to invest in electron source development, to improve the emittance from 0.5 to 0.1 so that we can beat the Germans.
What are the sources of the kinks?
Huh?
There are kinks.
Say it again? Kinks.
Yeah.
Like this, yeah, because you improve, but then at some point the undulator is what it is, right? So then you can't radiate, with 8 GeV, right? This basically, with 8 GeV you're not going to be able to radiate at frequency larger. Yeah, you're limited by that. So this is for existing system. I just have 2 slides and then I'm concluding. Where brightness. This is one case in which brightness can actually help for XFEL. Another one is efficiency. We just had a workshop like a couple, month and a half ago, 2 months ago, at UCLA in discussing high efficiency energy extraction. So in this case, when the FEL is typically saturates at some point, the efficiency is limited to Rho. What you can do in order to avoid that, you can taper the undulator so the resonant condition will change along the undulator. You can keep extracting energy from the beam. In this case, the scalings are different, and a higher brightness beam will greatly help in improving the extraction efficiency. The other one is something that the UCLA we've been very fond of in the last 5-10 years, is this 5th generation light sources. As I was saying, a smaller emittance will let you radiate a shorter wavelength with a lower energy beam. So this is trying to generate, trying to build a XFEL which is not as long as the SLAX Linac, but make it smaller, for example, in the level at which you can fit in a university laboratory or something like that. In order to do that, certainly you need very high brightness electron sources because you need to take advantage at all cases, in all points, of this improved brightness and improved emission. So these are the conclusions. High brightness electron sources have certainly played an enabling role in the development of X-ray FELs. And electron sources remains one of the major challenges for future FEL-based light sources, especially the high repetition rate ones. Significant improvements of beam brightness, if you can take advantage of that, you get larger Rho, basically, so you can get a higher energy photon, larger X-ray power, shorter X-ray pulses because the bandwidth can be larger, and in general, better energy transfer efficiency. And compact XFEL can be enabled by ultra-high brightness electron beam. In order to take advantage of the improved source performances, an existing system would typically need to be redesigned or reconfigured. That's it.
I have a question. Might be naive, and you might have covered it. I might have missed it. But I was very curious, because usually when I think of laser, I think of a quantum transition. And I noticed your entire analysis was classical
Absolutely,
E&M. So does the quantum regime come in at any point, or is that relevant? Or?
So yeah, the quantum, basically you can think about these are transition between free electron states. That's the way to, basically the electrons is emitting a little bit of a quantum of radiation, if you think about it.
But it's a continuum.
But it's in the continuum. So when does the quantum effect come into place? It's a particular limit of the XFEL in which quantum effects come into place. It's when the quantum of the radiation that you are emitting is significant compared to the bandwidth of the system. Right? Because in that case, the discreteness of the emission now starts to play a role. You emit one quantum and you get the electrons out. This is the quantum FEL regime, which has been analyzed and studied.
Are we like miles away from that?
Basically, in terms of experimental parameter, in order to access that, you either need to radiate, you need to radiate a very short wavelength with a low energy beam. Or, it depends on the relationship between the energy of the beam and the energy of the photons that you're emitting. So in terms of experiment, we're far away, miles away. But there is people that are thinking, because for futuristic controller, like very short wavelength controller, then this regime might start playing a role.
I have an economic question about the compact XFEL of future.
Mm-hmm.
So, universities, not routinely, but elite universities, to buy a $10 million microscope for Lena and David, that's quite doable. So, and there are these.
Steve and anything he drops, we pick.
Yeah. So, and NSF now has a very big initiative on mid-range, equipment up to 50 million that's coming down the pike. So, what's for people who are really working on these amazing new devices? I mean, make a 10-meter machine. What's pricing or something like that? Just take a guess. Or,
Well, I mean, the idea is that, of course, the research, this is not something that, there is a field of people trying to get this in place. And the goal, of course, is to fit it in something that not only will fit in space, but it will fit economically.
Yeah.
So put it in the order of 10 million or so, on that order, right? In general, like for example, the drive of this would be, for example, a big laser system, which you can get for a few millions or something like that. And then, the order is certainly not different than a large NSF scale. And in fact, those are the kind of proposals that are being sent around in this
So
field.
it's not 100 million, it's 10.
No, 100 million would be a national lab. It may be the size would be a university, but no university will afford it. So I think maybe Jenny wants to make a comment.
I want to make a comment on this because actually we submitted a proposal to NSF that was in sort of a prototype. It wasn't the real machine. It wasn't the real machine. It was something that has components of the real machine, and it was sold to NSF as an MRI for basically doing the fundamental training of students and development of the sort of pedagogical sides of the field. It wasn't, this is a user facility that's going to create photons. Now, since then, I've developed a much more sophisticated proposal that's at the white paper stage, and it's worth sort of commenting on in the context of Pietro's presentation and also in the CBB context. You start with a very high brightness photo injector that's based on new technology that we actually made the first jump in understanding how it works through CBB funding over the last year and a half. And so if you look at the numerically, since Pietro put in sort of relevant numbers, you have sort of micron scale emittances that allowed us to make the free electron laser to begin with, the XFEL. Now we can have emittances that are a factor of 20 smaller than that. That changes everything. For all the reasons Pietro said, everything shrinks down. Using the same technology that we use for this ultra-high field injector, it's a cryogenic copper approach, we can make the LINAC 8 meters long. We operate at 8 JEV. We have some basically X-ray FEL that almost fits in this room. And we costed it out, it's about $20 million. And this one has the nice feature of the fact that pretty much everything exists. We just have to put it together. So without invoking, future plasma accelerator miracles and so forth, we have a path now, I think.
I think we should have a break. When should we?
Yeah, so we'll have a, 5-minute break. That's because 10:25 we'll take a group photo. Just outside of there are stairs. So we'll gather together and take one photo, and we'll start at 10:30. So be as fast as you can. And coherent as you can, like XFEL.
10 minutes.
It's not a, nobody laughs.
I got it.
You got it?
I got it.
I tried. It's a lie, my best.
So we're going.